Welcome to Math 1342, Elementary Statistical Methods at Dallas College. I'm Professor Michael Bailey, and I'm going to be starting off this lecture about our statistics. You can see our textbook here, which is Statistics Informed Decisions Using Data by Michael Sullivan. And yes, that actually does look like me, and it pretty much sums up my lack there of style. All right, let's get started. So one of the things I want to talk about this course is some resources that you have, specifically what you can use online. We are using MyLab Statistics, which is a Pearson product that goes along with our textbook, and in there a very powerful tool is StatCrunch, and this is sort of like Excel but specifically designed for statistics and has many functions. You will be able to use StatCrunch on all the tests throughout this course, so taking some tutorials online, getting as familiar as possible to StatCrunch is wise as soon as possible. All of the data that's used in this course, in the textbook and in MyLab Statistics, is also available in StatCrunch or can be downloaded to use in Excel or elsewhere. And most of the data is actual real data from studies and other statistical research that's been done. You also have the Student Solutions Manual in eCampus, and this gives you worked out step-by-step solutions to all the odd-numbered text problems, all the odd-numbered problems in the back of each section in the text, in the electronic text that you have access to. Notice that you have all the solutions, odds and evens, for both the chapter reviews and chapter tests that are at the end of each chapter in the book. Finally, a really powerful thing for a lot of students who don't like to read the text is that in eCampus, as part of MyLab Statistics, they give you kind of the cliff notes of each section. I know that for chapter 1, there's 21 pages of notes that kind of break it down. And again, these are like cliff notes, and these are found in eCampus on the same pages where you link to the MyLab Statistics. If you look down, you'll see classroom notes. And you can download these and print them off so that they can supplement any notes that you're taking as well. So let's get started. In Chapter 1.1, Introduction to the Practice of Statistics, we're going to go through 5 different objectives. First, to understand what statistic and statistical thinking is, to explain the process of statistics. I'm going to start with distinguishing between qualitative and quantitative variables, distinguishing between discrete and continuous variables, and determining the level of measurement of a variable. So let's start off. What is statistics? Many people say that statistics is numbers. After all, we are bombarded with by numbers that supposedly represent how we feel and who we are. And a lot of times we're bombarded with qualitative language about numbers, like this is the largest increase ever, or the highest temperatures in 100 years, or whatever. And so those are qualitative measures that don't really give us the quantitative insight into what's the difference here. We often hear this, especially on the news and in media. The stock market plummeted, which gives a sense that it really fell from a high height. But if you looked at the statistical or quantitative data, you may see that it only had a 0.5% drop. Now, if someone said my pay had plummeted, I would think that that was more of a drop than 0.5%. So you have to be really careful, and that's one of the powers of statistical knowledge, is that we know that if we use numbers and we use statistical reporting techniques, we get a more accurate picture of what's going on, not a manipulative picture, which is using more of that qualitative data. Another interesting consideration is the facts we hear or read is that we often get 2 different sources reporting different results. For example, in your text, it talks about American beliefs, and so it asks, is it possible that Americans' belief about something would drop by 5% in only 1 week? Of course, depending upon what happens, this is possible, but really they were talking about how can two different sources report really different numbers. And so statistics, when you look at, when you have the knowledge about statistics, you can look at how the studies were done, what the audiences were, what the populations responding were, and how they did the statistics or the study, and that can give you into some insight into which may be more valid or not. So statistics can definitely help you kind of weed through some things as far as different or contradictory numbers, if you will. So our formal definition is that statistics is the science of collecting, organizing, summarizing, and analyzing information to draw conclusions or answer questions. In addition, statistics is about providing a measure of confidence in any conclusions. And this is really important because not only are you reporting all these numbers and saying things about them, it's to use, this last part is about using some common sense about how well you believe in the information that you're reporting that you got in your study. So, for example, if we wanted to know about the popularity of Italian restaurants or something, and we only interviewed people who were sitting in Italian restaurants, well, common sense tells us that if they're already in that restaurant, they probably like that food. So it's probably not a good population that we used to study when we got that 95% of all people like Italian food because our population was skewed. So this last part about, talking about our confidence in those measures is really important about, like, if we got high numbers or low numbers, what do we think about that? And really thinking through not only common sense, but logically, what do those results mean and how comfortable and confident are we in their accuracy of what they're implying? So let's break that definition down into 4 parts. I love outlines more than I love paragraphs. I think it's easier to digest, easier to remember. And so this is really about collecting information and then organizing it and summarizing it in some way. Now, going back to the collection of information, like what I just mentioned about the Italian restaurants, hopefully you'd recognize that only interviewing people in an Italian restaurant about the popularity of Italian food is a bad collection of data. So not only does it reflect on our confidence in our study, but hopefully using common sense throughout, we can think through, okay, this is not a good population to get an accurate picture of all people's love of this or whatever. Second, once we've gathered all that data, we have to organize and summarize it. And here's where I like to think of it as the first part is about data, just getting raw data. Do you like this? Do you not like this? Do you use this? Do you not use this? How many times do you use this? Etc. How much money do you make? Whatever the data is. The second part is what I call synthesizing it into information. What are the implications of all of this data? And so how we organize it is like maybe putting it into charts, putting it into a pie chart or a bar chart, comparing different groups, maybe finding all the women who answered one way or all the men who answered one way or all a certain ethnic group answered, how did they answer? And doing some of these comparisons. Now, the part of that is analysis, but part of us doing good analysis, step 3, is how we organize the information to kind of let us see what's going on. And so while the design and collection of the information is key, step 2 and 3 are really vital. Sometimes just mixing up your spreadsheets, your Excel, can give you different insights, and just building random charts sometimes visually, especially like pie charts and bar charts, can really, since they're one of the most visual tools that we have in mathematics, we're so used to seeing charts and interpreting that data relatively quickly that it can really help us draw some conclusions. So 2 and 3 are really vital. The information, then number 3, the information is analyzed to draw conclusions or answer specific questions. And then the last thing is that the results should be reported using some measure that represents how convinced we are that our conclusions reflect reality. So again, we might say here, while our study showed that 95% of people like Italian food or prefer Italian food, we realized that the population and the sites for collecting the data may have been skewed since we only were in Italian restaurants. So we believe this study should be done. A lot of times this last thing also includes future action. So we're going to redo this study and, pick different sites or neutral sites or whatever. So an important part of this is understanding what is data. A dictionary definition is a fact or proposition used to draw a conclusion or make a decision. Data can be numerical, such as in height, or it can be non-numerical, such as in gender. In either case, data describes characteristic of an individual. Analysis of data can lead to powerful results. Data can be used to offset what we call anecdotal claims. This is when you're just talking and, they said, or I heard that, etc. Here we have such a claim, the suggestion that cellular telephones can cause brain cancer. And your text implies, and it uses example 1 and 2 for additional referencing, that after careful collecting and analyzing data regarding this, it was determined that there was no link. The problem is that you hear something like this, such a claim, and someone may even try to have used statistics, or they might have said a report suggested. But the analysis of this is really important, both what data was collected, who it was collected from, and then how they reported that data or summarized it to do the analysis. Because data are powerful, they can be dangerous when misused. This usually occurs, like we see it a lot, in news feeds, in talk shows, in Facebook, etc. And especially when they use poll questions, where they might ask people to call in or click in to respond. Well, most likely the individuals who use this data are those who have a strong opinion. And because of that, the group that is responding, your population of your study, is not likely to be really representative of people in general. So almost all of these polls are not really that meaningful because they don't use a good sample population. Whenever we look at data, we should be mindful of where that data comes from and even how it was collected, the questions that were asked, etc. Even when data tells us that a relation exists, we need to investigate. Your book has a cited study here that's a really great example. They use a study that showed that breastfed children have higher IQs than those who were not breastfed. But does this study mean that a mother who breastfeeds her child will increase the child's IQ? We see studies and things like this all the time on the news that tell us about a relationship that exists, and then the implication is if we do whatever that first part of the relation is, then we will have the result that the relationship documents. This is an example of something called correlation versus causation. Causation means that if one event happens, it leads to or causes the other effect. Correlation means that there's just some relationship here, but it may not be causative. It may not be the reason or the catalyst that caused the effect. So does this study actually mean that a mother who breastfeeds her child will increase the child's IQ? Not necessarily. It may be that some factor other than breastfeeding contributes to the IQ of the children. And this is the things that you would want to investigate. Specifically, in this case, it turns out that mothers who breastfeed already generally have higher IQs than those who do not breastfeed. Therefore, it may be the genetics that's passed between the mother and child versus this habit or this practice of breastfeeding. This illustrates a really powerful idea in statistics called the lurking variable. And a good statistical study will have a way of dealing with lurking variables. And that's really your objective as a statistician, looking, or even someone looking at this report, is to try to figure out, are there things in here that we may not have considered that are different than our conclusions. And again, a question you always want to be asking yourself is, just because a relation exists doesn't mean that it's a causative. Is it causative or is it correlative? Is it just correlating? So it may seem a little bit mind-boggling that there's so many uncertainties. For example, typically when you take a math course, when you solve the problem correctly, you know that you can report the result with 100% certainty. In statistics, when a problem is solved, the results do not have 100% certainty. Uncertain results can seem really disturbing now, but as we go through the course, hopefully the knowledge and learning that you get will make you feel more comfortable with the uncertainty and in some ways even more powerful. But without certainty, how can statistics be useful? What happens is, as we just saw, statistics can provide an understanding of the world around us, because if we recognize the variability and also the relations between two different things, we don't automatically agree with everything that we hear, because we know that there may be more things going on, as we saw in the example with the breastfeeding and IQs, as we saw in the example with cell phones causing brain cancer. I've also heard it causing other kinds of cancer if you keep it in your pocket, etc. So statistics can provide us some understanding of how data works, and that there may be relations that aren't causative. And we heard of this new term, the lurking variable. So even just knowing that, it should even immediately, if you get this in your mindset, when you're watching news and other things or looking at Facebook, not to just accept what people are saying without understanding the statistical study, the statistical data, and even the analysis, how it was done, the population. This is going to provide you with context, a larger context into issues. And this is very personal. It's not just about watching the news. It's about your own life, we are inundated with marketing messaging. Did you even know where the recommendation that that a gentleman should buy his fiancée a diamond engagement ring, which is worth 2 months of his salary? Guess who came up with that? The De Beers company, the original company that had the greatest market share of diamonds in the world. Well, of course they want you to spend more money. Of course they want you to spend 2 months of income on that. And what is now kind of generally accepted as kind of a practice, if you ask many brides, I bet they know this, was all marketing done by the company who stood to benefit from it. So statistics, even just the general knowledge of this, will help you become a better citizen. It will help you be a stronger consumer, to put your money where you want to put your money, and it'll help you to be a much more critical and statistical thinker. And recognizing that you need to be really cautious when you hear data and reported as causative and conclusions, or this is what you are supposed to do. You are supposed to spend 2 months' salary on an engagement ring. Is that wise? Only you can really decide. And knowing where that comes from, again, where does this study come from, can give you a better insight into that. So we're about halfway through the lecture. This is a rather long lecture. And it's important for you to remember that, if you sit too long in something, that your brain is going to need a break every now and then. And so it's important to take breaks while you're doing your homework or while you're watching these videos. That may mean getting up and walking outside, getting a drink, just doing something different that's kind of like a shower for your brain. So just take a few breaths, if you will, or hit the pause button and go out, like I said, and get a drink. Not all of these videos are going to be really long, but if they tend to go more than 30 or 40 minutes, right around that part, I usually try to put a take a break in here and maybe ask you some kind of question, or read a poem or something that just kind of takes you out of the math for a minute and lets you do something else. And this is really important. So again, I'd say get up and take at least a 5-minute break, hit pause, and then come back and finish this lecture. So let's look at the next kind of objective of this chapter, which was to explain the process of statistics. And let's do this by using the example in your text. Consider the following scenario. You're walking down the street and notice that a person walking in front of you drops $100. Nobody seems to notice the $100 except you. Since you could keep the money without anyone knowing, would you keep the money or return it to the owner? You can kind of think about that for yourself. But then, as you're doing this, you might think, I wonder what people would do generally. Would they keep the money? Would they, give it back, etc.? So you might want to use this scenario as a gauge for morality of students at your school or at work or wherever you are, by trying to determine the percent of students who would return the money. How might we do this? Well, let's look at that and look at some process for using statistics to figure this out. So thinking about that last study about students returning the $100 or keeping it. So the entire group to be studied is called the population. So in this, it would be all students at a specific university from that last study. An individual is a person or object that is a member of the population being studied. So that could be anyone who is a student at that college. A sample is a subset of the population that is being studied. And we use samples in statistics because it's really almost, especially in larger groups, it's very difficult to survey or to study everyone. So we take a sample, a smaller grouping of that entire population, to try to figure out what's going on, and then to, kind of using analysis to relate that to the larger population. A statistic is a numerical summary based on a sample. So again, the sample is a smaller grouping of the population, and a numerical summary a statistic is a numerical summary based on the sample. So if we did a study with 100 students and we found out that 52% would return it, that 52% would be a statistic. 52% of the sampled population would return the money. Descriptive statistics consists of organizing and summarizing data, and this would be numerical summaries, tables, graphs, etc. So instead of your first collection of data might be just finding out, would you return it, yes or no. Compiling this then into what's happening in the sample or in the grouping, finding out how many yeses versus nos in tables, etc., and then relating it in terms of percents, is that kind of descriptive statistics. Descriptive statistics. Okay. Inferential statistics is when we take the results from our study of the sample and extend them to the population. And this also kind of goes back to the reliability of the results, or our confidence in the results. In your text, it says, we have 95% confidence that 78 to 82% of students, of all students of the population, would return this money. Okay. A parameter is a numerical summary of a population. Now, the difference between a parameter and statistic is what it's based on. So notice the statistic is based on a sample, and a parameter is based on the entire population. So we might say 78% of the entire student body would return the money. That's a pretty strong statement because it's not giving any kind of leeway. It's also not giving any kind of indication of how confident I am of that statistic. From your text is example 2, parameter versus statistics. Suppose 48.2% of all students on your campus own a car. Is that a statistic or a parameter? Suppose a sample of 100 students is obtained, and from this sample we find that 46% own a car. Is that a statistic or a parameter? Well, remember, a parameter is based on all the entire population, where the statistic is based on a sample. So the first example is a parameter because it's a numerical summary of a population, where the second statistics, or the second number there, represents a statistic because it is a numerical summary of a sample. So here's a really good example of the process of statistics, which is a study called Trust Your Neighbor. So the Pew Research conducted a poll and asked, do you trust all or most of your neighbors? The following process allowed the researchers to conduct their study to see how do people trust their neighbors. So the first thing they did was to identify the research objective. The researchers wanted to determine the percentage of adult Americans who trust all or most of their neighbors. Therefore, the population was adult Americans. Step 2, collect the data needed to answer the question posed in step 1. As we mentioned before about population versus sample, it's unreasonable to expect to survey the more than 200 million adult Americans to determine whether they trust their neighbors or not. So the researchers surveyed a sample of 1,628 adult Americans. Of those surveyed, 847 stated that they trust all or most of their neighbors. The next step was to describe that data, to take that data and kind of summarize it in tables and charts, etc., in some way that makes that data more useful. In this case, it was that 50% of the sample said that they trust all or most of their neighbors. This is a descriptive statistics, but because it is a summary of the sample data. The sample data would be John Doe trusts more, all or most, etc., and going down the list. And finally, to perform an inference. And this is again taking it from the sample to the entire population. Pew Research wanted to extend the results to all adult Americans. When generalizing results from a sample to a population, results are uncertain. To account for this uncertainty, Pew reported a 2.5% margin of error. This means Pew feels fairly certain, in fact 95% certain, that the percentage of all adult Americans who trust all or most of their neighbors is somewhere between 49.5%, which equals 52% minus 2.5, and 54.5, which is of course that same 2.5 difference, but now added to that original discovered statistic. I think this is a great example to kind of see that process overall and to make it more tangible to you if you haven't experienced statistics before. So let's look at our next objective for this section, which is to distinguish between qualitative and quantitative variables. Your book actually uses tomatoes for an example. So variables are simply the characteristics of the individuals within a population. It's important to remember that variables vary. For example, the weight. Not every tomato has the same weight. Sometimes they don't vary, like you might be talking about the species or something. So qualitative or categorical variables allow for classification of individuals based on some attribute or characteristic. For example, we may only want to consider red tomatoes, or we might want to consider different species of a tomato, etc. These are qualitative or categorical. So it's based on an attribute or a characteristic. Quantitative, like the name suggests, are numerical measures of individuals. The values of the quantitative variable can be added or subtracted and provide meaningful results. Some examples might be the weight of the tomato, the diameter of the tomato, maybe the number of tomatoes per plant, etc. Okay. Example 3, distinguish between qualitative and quantitative variables. Determine whether the following variables are qualitative or quantitative: gender, temperature, number of days during past week that a college student studied, and zip code. Throughout this series of videos, you'll often see something that comes in and looks like this, a pair of paws. And it's my recommendation that you actually pause the video, try this problem or the example on your own, and then hit play again once you finish and think that you have a valid answer. So go ahead and try that, hit the pause button, and see what you come up with for these 4 classifications, and make sure you're on target. So the first one is gender. Of course, this is qualitative. There are no numbers involved. The second one, temperature, does involve numbers, and numbers that can be added and subtracted, etc., to make some meaningful inferences. The number of days during the past week that a college student studied, these can also be added or subtracted and combined in a quantitative way, a numerical way. The last one's a little more confusing, right? Because it's a zip code, which is a numerical format, but it's not a number per se that we would manipulate. It's really more indicative of where you live, an area or region. So this is also qualitative, not quantitative. So hopefully you paused and you got those right, and can see kind of what's coming in the future as far as these pause and recommendation for you to try some of these. So our next objective in this section is to distinguish between discrete and continuous variables. And from the image that you're seeing there, you can see that discrete and continuous variables are classifications of quantitative variables, not qualitative. A discrete variable is a quantitative variable that has either a finite number of possible values or a countable number of possible values. The term countable means the values result from counting. Think of our counting numbers, 0, 1, 2, 3, and so on. A discrete variable cannot take on every possible value between any 2 possible values. For example, here we can't count to 1.5, etc. So discretes are finite number of possible values, or a countable number. Whereas continuous is a quantitative variable that has an infinite number of possible values it can take on and can be measured to any desired level of accuracy. So here we have another example. Example 4, to distinguish discrete versus continuous variables. Determine whether the quantitative variables are discrete or continuous. Again, you see a little pause print down in the bottom right. So go ahead and hit pause and answer these 3 questions, whether they are discrete or continuous. I'm assuming you're hitting pause now, and I'm going to continue forward. The number of heads obtained after flipping a coin 5 times. This is very simple to calculate. We can just do the experiment 5 times and count the number of heads, and we can see that there are 6 possible answers. I could have 0 heads, 1 head, 2 head, 3 head, 4 head, or 5 heads after flipping 5 times. So there's 6 possible answers. That is a finite possible number of results, and so this is discrete. The number of cars that arrive at a specific McDonald's drive-through between 12 and 1 p.m. Here again, I can sit there and observe and literally just count the numbers, so this is discrete. The distance a 2019 Toyota Prius can travel in city driving conditions with a full tank of gas. Well, I could have different Toyota Priuses. I don't know the city. I could have different conditions in the city. I could have different measures from the different Toyotas. And I could also measure the distance in different units of measurements from miles, etc. So this is a continuous. There's a lot of different potential answers there, and really it's an unlimited number or an infinite number of potential answers. So we have another example here. Again, another chance for you to pause and see how your understanding is. Distinguish between variables and data. The table represents a group of selected countries and information regarding these countries as of July 2018. Identify the individuals, the variables, and data in the table. So again, hit pause and try to do this. Think about what are the individuals in this information, in this data, what is the variables, and what is the data. Okay? All right. So remember, an individual is an object or person for whom we wish to obtain data. The variables are the characteristics of the individuals, and the data are the specific values of the variables. So here we can see the answer to this problem by colors. The individuals are in yellow, variables in green, and the data's in orange. The individuals, or what we're trying to get information about, are specifically the countries in the table, like Australia, Canada, etc. The variables, remember, these are the types or the characteristics of the individuals. So these are all the headings of the columns because that's what we're gathering data on, specifically government type, life expectancy, and population. We can see that government type is qualitative because it has information and that's non-numeric. Life expectancy and population are both numeric information, and so they're quantitative. Life expectancy, because notice that we can't count it, but we can measure it, and it's continuous because there's really an infinite number of choices. It could be, especially since you have a decimal place in here. Okay. However, the population, even though there's decimals in there, notice these are in millions. Okay. So we can actually count them, how many people are in a place, etc. So this is a discrete variable. And finally, the observations are the data. For example, the following data corresponds to the individual Poland. Here we have, let me pull up, sorry about that. Poland is a republic with an average life expectancy of 77.8 years and a population of 38.5 million people. The life expectancy of 77.8 years is an instance of quantitative data resulting from observing the value of the quantitative variable. Okay, so the data republic would be a qualitative data because it's a qualitative variable. Okay, I know that there's a lot of gradations here, so that's why I'm giving you more examples, and hopefully you're kind of catching on to this and taking good notes. So our last objective for section 1 is to determine the level of measurement of a variable. We have two qualitative measurements, and those are nominal and ordinal. Nominal in Latin means to name something, and ordinal means to order something. And so that can help us distinguish between these qualitative measurements. So the nominal level of measurement, it's when the variables name, label, or categorize something. Well, of course, that happens for really any kind of variable because that's what a variable is some way of creating a category or characteristic. But for nominal level of measurement, the naming scheme, whatever the characteristic is, doesn't allow for the values of the variable to be arranged in any ranked or specific order. Sure, you can put things in alphabetical order, but that's not really a statistical ordering of something that ranks importance, etc. So ranking is really important here as well as specific order. Ordinal in Latin means to order things, and so that's the real difference here. It has those same characteristics to name, label, or categorize. However, the variables now can be put in a ranked order, okay? And again, these are both qualitative measurements. The quantitative measurements are interval and ratio level. So a variable is at an interval level. Again, it has those same properties, name, label, or categorize. And the differences in the values of the variables have meaning. Here, a value of 0 does not mean the absence of a quantity. Arithmetic operations, such as addition and subtraction, can also be performed on these values. Okay? The final level of measurement is the ratio level of measurement, and it's that if it again has those same things as name, label, or categorize, and those values have meaning like in the interval level. But here a value of 0 means the absence of the quantity. So if you see 0 there, there is no measurable quantity for that variable, and arithmetic operations like multiplication and division can be performed on these values of the variable. And that makes sense when you think of a ratio, because what is a ratio? It's really a fraction, which is a division problem. So here we have our last example and our last slide for the first section. Example 6, determine measurement level. For each of the following variables, determine the level of measurement: gender, temperature, number of days during past week that college students studied, and letter grade earned in your statistics class. So again, hit pause and try these out and see if you can identify the 4 different types of levels of measurement for each of these. Hit pause, and then when you're ready, come back and hit play. So gender is going to be male or female. There isn't really any way to rank those. So this is just a naming thing, so this would be nominal as it cannot be ranked. Now temperature is numeric in order, so it's quantitative. We can rank temperature. And so the other question is, what does 0 mean? Does 0 mean there is no temperature? Well, no, 0 degrees is actually a temperature. It doesn't mean the absence of heat, it's just some measurement of heat. So since 0 does indeed have a indication or a value for that variable, then this would be interval, because it's quantitative, it can be ranked, and 0 does have meaning. The number of days during the past week that a college student studied. Now here, again, we have a number, so it's quantitative, so we know it's either interval or ratio. Can we multiply them or rank them? Of course we can. We know that studying 4 days a week is double the amount of studying 2 days, so that's a sort of a ratio or a multiplication of those values that gives some kind of ranking. Also, we could say that 2 out of 7, so it also is indicative of a ratio as well. So we have quantitative, we have ratios, and we also know that 0 means that there wasn't anything in this category. 0 numbers of days, meaning the student did not study. So it doesn't really have meaning here. It means that there's the absence of that variable. And finally, the letter grade earned in your statistics class. Well, here we have not a numeric value, but a naming value for a grade. So this is qualitative. But of course, as we know, grades of A, B, C, D, and F, we can rank them in some kind of order that has meaning. So this is a case where we have an ordinal level of measurement, because we do have a name, but we can rank it. Okay, I know this is a little bit confusing, and if you go to the text for this problem, they do even more in-depth explanations of each of these. Okay, so I know this was a long lecture. Hopefully not all of them will be this long, and hopefully this is a good start for the class for you.